I'm Wolf McNally, lead researcher for Blockchain Commons. This presentation is Gordian Envelope, Elision, and controller documents. Blockchain Commons is a proudly not-for-profit social benefit corporation domiciled in Wyoming, but operating worldwide. We have a strong commitment to open source and a defensive patent strategy. Anyone can use or improve our tools, and no one can take them away. We engage in a variety of activities working with various communities, including the development of guidelines, specifications, reference implementations of libraries, and apps that demonstrate the use of our technologies. We're sponsor-supported, so please consider becoming a sustaining sponsor, a GitHub sponsor, or making a one-time BTC Pay donation. And also join the conversation at blockchaincommons.com. This includes our discussion forums on GitHub, low-volume announcements via email, various Signal groups, our monthly Gordian developer meetings on the first Wednesday, and also special interest group meetings. For example, our Frost implementers, Silicon Salon for hardware developers, and more. I'm going to start with a quick recap of some of our technologies that are relevant to this presentation. Our intro materials include videos, particularly the Envelope playlist on youtube.com/@blockchaincommons. This includes a brief Gordian Envelope teaser. And then we have our much more extensive Understanding Gordian Envelope Parts 1 and 2 videos, which are essential watching if you're considering adopting the technologies. Our websites have a lot of information and other resources you're going to want, and our main portal for envelope development is at developer.blockchaincommons.com/envelope. Envelope is a smart document system built on deterministic CBOR, or DCBOR. CBOR is the Concise Binary Object Representation that you can think of as like JSON, but binary. It's also concise, self-describing, good for IoT and constrained environments, and platform and language agnostic. It's got many implementations, including our own DCBOR implementations. DCBOR is deterministic at the binary level up. An example of what this means is there's only one way to encode each numeric value. Unlike JSON, where you can encode 0 numerous ways, there's only one value for 0 in DCBOR. Strings are always Unicode normalization form C, or NFC. Map or dictionary keys are automatically sorted. There's never a context required to sort, and there's never a need to canonicalize as a separate step. Gordian Envelope defines a very simple semantic structure based on semantic triples. Triples are subject, predicate, object. This is an example of what that schematically looks like in what we call envelope notation, with the subject first, a pair of square brackets, and then a series of predicate-object pairs called assertions. You should note that this is not typically the meaning of subject used in the verifiable credentials domain, which is a person or organization about which claims are made. But in some cases it can be. Gordian Envelope is an enumerated type with 5 basic cases. Each of these cases is itself an envelope. The first case is leaf. This is any encoded CBOR data that can have any structure you like. The second case is node. This is a subject envelope and one or more assertion envelopes. An assertion is an envelope that pairs a predicate and an object. An elided case is a digest left behind when a whole branch of the tree is replaced with just this node, which only holds that subtree's top-level digest. And the wrap node has as its sole child an entire envelope, and this allows you to add meta-assertions to the wrapped envelope. You'll see several examples of that in this presentation. There are also 3 extension cases, which aren't part of the basic internet draft that is currently working its way through the IETF. There's the encrypted case, which encrypts an entire branch of the tree using the IETF CHA-CHA-20 Poly 1305 symmetric encryption algorithm. There's the known value. Many JSON documents use long and often repeated URLs to convey certain concepts. Known value is a 64-bit integer space, which defines a library of concepts, including concepts from the RDF space, the OWL space, and any other semantic space that the community wishes to register. The compressed node uses the deflate algorithm to take a branch of the envelope tree and compress it into a single node. One thing to emphasize is that envelopes are a recursive structure. We like to say that it's envelopes all the way down. Envelopes containing envelopes containing envelopes. How does that actually look? Here's an envelope tree. You can see it has a single root, and the internal nodes are red. They are nodes that have one or more child nodes, and then the leaf nodes are blue. Every node in an envelope's tree is itself an envelope. What do I mean by that? Well, it's one of those 8 cases I mentioned. A node and assertion cases have child nodes. As you can see, the node case highlighted here has a subject child node and 2 assertion child nodes. In fact, 3, one goes off the bottom there. The assertion nodes have a predicate and an object child. Any child node without assertions can be replaced by a node with assertions. This includes predicates. So if you see the assertion there, where the predicate there is the known object dereferenced via, that predicate can actually be replaced by a node. In other words, you can have assertions on predicates. Even a complete assertion can become the subject of a node. So either of those assertions you see there can be replaced by node cases, in which case the assertion itself becomes the subject, and then additional assertions can be added to the assertion. This allows for deeply rich metadata. Every node in the tree has a unique digest, and certain transformations preserve the top-level digest, and you've seen the 3 that do. These are elision, encryption, and compression. For controller documents, holder-based elision is the real game changer. This lets you only transmit the data you want. Signatures on the document are preserved as long as the digest tree maintains proof of the elided data. And inclusion proofs allow you to reveal parts of the document later in a verifiable way. We call this progressive trust. Let's look at an example. Here is a Gordian envelope. It's a driver's license. The subject of the envelope is the driver's license number E2811029. And that subject has a series of assertions on it. The entire envelope is wrapped. That's what the curly braces are. And then there's a meta assertion, which is the verified by signature. Note that the icons to the left of each of the lines is unique. That's called a life hash, and you can go to lifehash.info to learn more about that. That's another blockchain commons technology, which is open source and available to use. And we often use it in our apps and presentations to visualize any kind of cryptographic digest. So you see that the top level envelope, the meta envelope, signified by curly braces, has a unique digest. That signature itself is a signature of the digest. So as long as that digest remains the same in what is signed, then the signature remains valid. In a real-life scenario, we'd probably want to add salt to some of our fields. A salt is a short sequence of random numbers. Why do we do this? For example, if we take the digest of the word John, that's a pretty easily guessable digest. So we want to decorrelate the first name using an additional assertion, which is just random numbers. So you can see the additional life hashes to the left of the first ones. Those are the unique digests for that branch of the tree once it's been salted. Notice also the top level signature has changed. If what is signed changes, the signature will always change. We're going to keep it simple in this example by not dealing with the salt. So when we're asked to present a document for a particular purpose, for example, prove your date of birth from your photo, the holder can then elide the various fields that aren't relevant or necessary for the actual proof. In this case, the driver's license number is elided, as well as everything else not required to prove the date of birth from your photo. So the date of birth is there, the photo is there, the fact that it is a driver's license and who it's issued by, and the signature are all still there. The signature is created by the issuer. Notice that the actual top-level hash hasn't changed, and therefore the signature is still valid. At a later time, somebody might ask for an additional proof from the same document, for example, proving where you live. To do this, we create what's called an inclusion proof. In this case, the inclusion proof is just the single assertion that was elided before that matches the address. Inclusion proofs can just be the branch of the tree that was removed. Sometimes you have need of a more complex inclusion proof, and we'll see an example of this later in the presentation. One other technology using envelope that I want to touch on is the Gordian Sealed Transaction Protocol, or GSTP. Gordian envelopes can be used not just for data at rest, but also data on the wire. This is a peer-to-peer request-response-based protocol that uses Gordian envelope and has a couple rather unique features. It's designed for unreliable or insecure channels, including the internet, Bluetooth, NFC, Tor, and even the lowly QR code. Blockchain Commons has technology that allows you to put as much data as you like in a series of non-repeating QR codes. GSTP can be used to establish key agreement, exchange data, facilitate confidential backups, coordinate multi-sig sessions securely and without local state. And that's something we want to emphasize. So let me show you a quick example. This is what a GSTP request might look like. It has a unique ID, it has a function identifier and a series of arguments, and it also packages the sender's public key. The sender then signs the envelope with that key, and therefore this request can be used in a trust on first use or TOFU context where The receiver has never seen this key before, but at least it can know that whoever sent this key has the private key that goes with it. But GSTP requests and responses can also include what we call encrypted state continuations. As you can see, there are two continuations in this request, a sender continuation and a recipient continuation. The continuation mechanism is a way to offload state to the future without revealing it to the peer or the server. The sender continuation is a packet of data that I have encrypted back to myself as the sender that only I can read, but I'm sending it to the recipient. All they can do, since it's encrypted back to me, is send it back to me with their response. Meanwhile, the recipient continuation that I've included, it was sent to me encrypted from my correspondent, the recipient. And so all I can do is pass it back to them. This state can include anything that you might need, such as database cursors, and because you don't need to store it locally, it's very useful for either constrained environments or environments like server farms that need horizontal scaling. So we'd like to improve on controller documents using these technologies. There are several ways that have been proposed to do this. First of all, there's CBOR LD. There's also proposals for bespoke CBOR formats for controller documents. And finally, there's Gordian Envelope. And this is the format we like to propose. Why? Well, there's all the flexibility advantages we've already talked about, but holder-based elision, that's the real game changer. With DIDs, you have to reveal a method and a verification key. But with an envelope, you can elide additional keys or endpoints that aren't necessary. This is the principle of data minimization, which is important for various privacy and data retention regulations and policies. You can also verifiably reveal elided items at a later time. So here's a controller document reimagined as a Gordian envelope. This is an envelope which has a unique identifier and a series of keys. It's also signed by one of the permitted verifiers. In its unelided state, the signature, of course, verifies. And again, in real-life applications, we would salt anything that we wanted to avoid correlating. Keys themselves can be correlated across large numbers of documents, and so we might want to salt them. When we actually want to present the document for some purpose, we first elide it to remove everything that's not necessary. In this case, we want to reveal the signing public key, the agreement public key, and the endpoint for messaging. We also do this without disturbing the signature. In another case, we might want to elide all the assertions other than the signing public key and the signature, and so this only reveals that we have an identifier with a valid signature. Let's look more closely at the elided assertions. As before, each of these three elided assertions has its own unique digest that is left inside the document as an elided node. When we want to reveal at a later time one of those assertions, we need to produce an inclusion proof. The inclusion proof for the second assertion has to have a digest that matches that assertion. In fact, any envelope that matches this digest is the only thing globally that could possibly fit in that space, even when that envelope revealed is itself partially elided. Let's look at that. Here is an elided version of that assertion. All this reveals is the agreement public key. It doesn't even reveal the endpoint. It's possible to actually insert this elided document back into the original envelope, uneliding that branch of the tree, and the signature still verifies. So how would we integrate Gordian envelopes with existing infrastructure for controller documents? Here is a fragment of a controller document as an envelope that has a couple service endpoints that have been salted. We can elide these two endpoints, and then we can serialize and then base64 encode that CBOR serialization as a string. Now we can include this string in a JSON controller document with its own type of elided services. This allows us to reveal either of these endpoints at a later time in a completely verifiable way.